You better be prepared.
We chose the exact wrong time because Don is taking we have the literature test on Monday.
We didn't pick the exact wrong time. You might have picked the wrong time to start studying for the test, and that's your own fault. The test is test what you know. You could have known this stuff 3 weeks ago. You can know it now. That's your choice.
I'm perfectly knowing.
Huh? You're perfectly what?
Knowing.
You're
No.
perfectly knowing? Wow. Awesome. We got a perfect knower over here. Okay, Leibniz notation. Now we're going to be going over the derivative just like we did before. This time we're using Leibniz notation. And like I said, I've got a textbook here that I'm just going to go through that happens to use Leibniz notation. And it's not an analysis textbook like what we've been using, so it's not as rigorous.
Are we going to define what it is? We'll just go ahead.
We're going to define the derivative, starting with our definition of derivative. I'm going to come up with their definition of derivative. It's the same thing, you'll see. But so our definition of derivative, we said that's the limit. This is the derivative at
X naught as x goes to x naught.
Right. Approaches x naught of f of x
F of x naught.
minus f of x naught over x minus x naught. Okay? This is the derivative of f at x naught. So if we do, and you guys comfortable with delta x?
Change in x.
Yeah, it's a difference in x.
Okay.
In other words, we usually use delta x to represent a small distance in x. Right? So what's the distance between 9 and 6?
2.
3. How'd you do that? Minus. So this represents a difference or a distance, same thing. So if I let x, delta x equal x minus x naught, then that's the distance between these 2 points, right? Yeah. So now I'm going to rewrite this exact same thing, except for I'm going to use this delta x variable. So that's the limit as, now as x goes to x naught.
As delta x goes to 0.
Right. If delta x is equal to x minus x naught, as this approaches this, if I take the limit of both sides of this, the limit of this as x goes to x naught, and the limit of this as x goes to x naught. What's the limit of this as x goes to x naught?
X naught.
The limit of this is x naught. What's the limit of this?
Oh, 0.
0. So as x goes to x naught, delta x goes to 0. So that's the same thing as the limit as delta x goes to 0. As the distance between them goes to 0. Make sense so far?
Yeah.
F of x is now going to be, now remember, up here, well, I'll just write it down. So if delta x equals x minus x naught, then x equals what? It equals x naught plus delta x. Okay, so that's the limit as x naught plus delta x minus f of x naught all over x minus x naught is delta x. So this is how this book defines the derivative at x naught. Now they don't say the derivative at x naught, they say the derivative at x. So finally the last step is change how we name our variables. Make sense?
Hold on.
This is the derivative at x naught. The only reason up here we say the derivative at x naught is because we have an x and an x naught. So we need to distinguish between those. We no longer have an x in this equation. We just have x naught. So we can, instead of saying the limit at x naught, or the derivative at x naught, here's the derivative at x naught, here's the derivative at x.
So how does x plus delta x equal x?
No, that was for this. Now, if this is, look, x naught is just a point now, right? Instead of calling the point x naught, now call it x. Forget all the math that we did to derive this equation. Now we have this equation.
Okay.
This x here now represents something than this x here. Okay? So this is the definition I'm going to use because I'm not going to write x naught every time.
Okay.
You good?
Yeah.
Okay. So, once again, let's draw the picture to get intuition for what this is representing. if I've got some curve, and we've got a point x here, and a point x plus some distance, delta x plus the distance between them. Delta x is the distance between them, right? So x and x plus delta x, some distance. This point right here, the height of this point is going to be f of x, or in other words, y. I'm going to now use y's.
Okay.
Good?
Uh-huh.
This right here is f of x plus delta x. I'm going to call that is also equal to y plus our change in y. So now this distance right here is delta x, and this distance from here to here we're going to call delta y. You good with that?
Mm-hmm.
So up here I'm just going to call this point, this has a height of y plus delta y. And maybe I'll write this out what these were. Y was f of x, right? And y plus delta y was f of x plus delta x. Good?
Okay.
So now, plug in those renamings here. What does that give us? That gives a limit as delta x goes to 0 of f of x plus delta x is the same thing as y plus delta y, right?
Mm-hmm.
Minus y over delta x, which is equal to the limit as delta x goes to 0 of delta y over delta x.
Isn't that going to be, what? Also, that's not making sense to me because
Rise over run.
I know.
Change in height over change in distance.
But what's bugging me is delta x goes to 0. Because as delta x goes to 0, that number becomes massive.
Good point. As delta x goes to 0, what happens to delta y?
It becomes massive.
It goes to 0. As the distance between these 2 points goes to 0, the distance between these 2 points goes to 0.
Yeah, you're right.
If that wasn't the case, they would be continuous. Remember, one of our definitions for continuous is if the limit as x approaches x naught of f of x equals f of x naught, then they're continuous. What does this mean? Rewriting it in different terms. The limit as delta x goes to 0 of y is equal to y plus delta y.
Where's your x then?
Oops, did I write that backwards? Of y plus delta y is equal to y. The limit of this thing as delta x goes to 0
Right.
is equal to this thing, which means delta y goes to 0.
Right.
Because the limit of y is just y, so the limit of delta y is
0.
0. Good?
Mm-hmm.
So that's what we mean by continuous. Continuity implies as this goes to 0, this goes to 0. Has to be that way. Otherwise it wouldn't be continuous. Otherwise you'd have some number up here that wasn't 0 divided by something going to 0, blows up like you're saying. And the limit wouldn't exist. So good point. Okay, so are we good with this so far?
Yeah.
Now remember what we called this in our other notation. What did we call the derivative? We called it f prime of x. Right? That's Newton notation. Leibniz notation is we're going to call this dy dx.
Difference in y or what?
The limit as delta x goes to 0, delta y over delta x is dy dx. And the way that we often read this is the derivative of y with respect to x. Y was a function that had x's in it, and we took the derivative of it with respect to x. What do we mean by with respect to x? The things that with x's in it is what we were differentiating. So if I say y is equal to, let's just see an example really quick, x cubed plus 2x. You know how to take the derivative of this thing, right? What's the derivative of 3x?
It's 3x squared.
Or, yeah, so 3x, x cubed is 3x squared. And what's the derivative of this?
That's just 2x, or 2.
2. So dy dx, the derivative of y with respect to x, is equal to this thing. this was called f of x, then this right here is f prime of x.
Derivative of y with respect to x.
The derivative of y with respect to x is how we read this notation. How we read this notation is f prime of x.
So if it was x equals y cubed plus 2x, it would be dx over dy.
I mean, this symbol right here, for the purposes, the reason that Leibniz notation is great is because what if we also had plus v here? And we're taking the derivative of this thing.
Keep v where it is.
Is v, well, I won't get to that actually. That's constructive tangent. Ignore that whole train of thought. For the purposes of today, this symbol is identical to this symbol. There's no difference between them.
Right.
Good? So, the limit as delta x, or as the limit as delta x goes to 0 of that is equal to that. Now notice y here is just a dummy variable. Y is just a function in terms of x. Right? I could have just as easily written u, no, I'm going to write u or y still, but all funky. If I say u is equal to 3x cubed, what is the derivative of u with respect to x?
9x squared.
9x squared. Let's get real crazy with it. What if I say that y is equal to 3u cubed? What is dy?
dy dx.
No. What's dy du?
9 u
Same thing. 9u squared. So the nice thing about Leibniz notation is it enables you to call the variables whatever you want as long as you're doing the derivative of an independent variable with respect, or the derivative of the dependent with respect to the independent. So you good with all these different ways of writing the same thing?
Mm-hmm.
Now, one more way that you might see his notation, instead of this, you might see it written this way. So let's say u is equal to x cubed. What's this equal to?
3x squared.
3x squared, exactly what you expect. Now, why did I bother writing that? Because sometimes we might skip over the u altogether. We might say, what's the derivative of x cubed with respect to x? You with me?
Just because u is x cubed, I see.
Right. And so now this is the exact same thing, 3x squared. So all that's Leibniz notation, a lot of different ways to do it.
Just for convenience.
I mean, you'll see why using different variables is useful when we get further down the road, in particularly the chain rule, but just here's a bunch of different notation. So we'll start going over whatever the book does. We'll go over a bunch of proofs that we've already done using Leibniz notation to help get you more comfortable with it and see it in the same context that you've seen the f primes. Because it's helpful to see Leibniz notation before we get to integrals, because as you know, when you get to integrals, you're dealing with dx a lot. Right?
Mm-hmm.
And there's a lot of shorthand ways that we write things that use those dy, dx, du's, d whatever. Like, for example, this is just motivating for Jacob, sorry James. You memorized integration by parts. The integral of u dv is equal to u times v minus the integral of v du.
Right.
Stuff like that. This kind of stuff makes a lot more sense once you know Leibniz notation. And it helps you make that connection, whereas otherwise, if we just went from our f primes to stuff like this, and you're like, what do you mean? So, that's why Leibniz notation is helpful before you do integrals, help you wrap your head around stuff like that. So, we know our definition of the derivative now. In short, it's limit as delta x goes to 0 of delta y over delta x, rise over run, right? So now let's do, which one does he want to do first? Okay, so now let's prove that y equal x to the n implies dy dx is equal to n times x to the n minus 1. Right? Something we already know how to do. Okay, so let's write this out. We're looking for the limit as delta x goes to 0 of, remember what y plus delta x equals. Y plus delta y is equal to f of x plus delta x, which in this context is equal to y plus delta y, or x plus delta x to the n. You follow that logic?
Yeah.
Did you say yeah? No. Y plus its change is going to be whatever the function spits out when you plug in x plus its change.
And that's
Which,
the function.
when this is a function, sorry, y is the same thing as f of x, right? If y is equal to x to the n, then y plus delta y is equal to x plus delta x to the n.
Yeah.
I'm just trying to help you see how you rewrite y plus delta y in terms of x plus delta x. Because you might have thought, okay, y is equal to x to the n, what's y plus delta y equal to? Oh, I don't know. Maybe it's equal to x to the n plus delta x to the n. What is it? Remember what y plus delta y represents. It represents f of x plus delta x. So you need to plug x plus delta x into the function, and that's what this is. Make sense? That's the tricky. I shouldn't say that. I think that's the trickiest part of wrapping your head all the way around Leibniz notation when it comes to taking a derivative. Remember what y plus delta y equals. It equals what you get when you plug x plus delta x into the function that you're talking about. Always remember that connection, because you're going to over and over again need to write out what this thing is. Because remember, our derivative is y plus delta y minus y over delta x. So it's y plus delta y minus y over delta x. Any of those steps feel weird? All caught up with where I am? Okay, perfect. So now we're going to do exactly what you think we're going to do. What are we going to do? If you say fact, I'm going to throw a mark at you.
Fact.
It is fact.
Good throw.
Lucky for you. I retired from the MLB. So my pitches are off. Anyways, what is this thing?
1 second, let me just think about it for 2 seconds. Is it
Oh,
N
binomial. If only I knew how to expand you.
Yeah.
Oh, binomial theorem, ring a bell?
No.
Yeah, that's
It better ring a bell. Holy moly. One of the first things we went over, x plus y to the n is equal to the sum as k equals 0 up to n of n choose k times x to the, doesn't matter which order you want to do, but we'll do x to the n minus k, y to the k. Binomial theorem, one of those basic theorems in all of math. Right?
What is n over k?
Remember the thing that we spent a whole week on in discrete math, proving this thing? Huh?
What does n over k mean?
N choose k? I won't give you a definition, I'll give you a mathematical formula. I guess you can think about this formula as a definition, but it's not a good definition because it's not very insightful. It's n factorial over n minus k factorial times k factorial. But really, it's the number of k element subsets you can get from an n element set. And this happens to give you that number, but this, what is that, isn't very, it's just a big computation. Anyways, this thing, whatever it is, right? Binomial expansion. Preliminary stuff. First week of class. This is one of the things we talked about. Maybe I'll push the second week, I don't know.
Told you, I hate.
Super basic right from the beginning. Two really basic things. This is this. This, not in parentheses, is this.
Right.
Whatever. These are two things that when you see, it's like Christmas. You're so happy about it. You know exactly what to do with those things. It's just obvious.
Dude,
You see that, you can expand it out. You see that, you can factor one out.
I forget how summations work. K equals 0 means you start.
Let's do some adding. Basic arithmetic, right?
Yeah.
Start with 1 plus 1. We'll start at k equals 0, and we'll go all the way to 2. We're going to do 1 plus 2 real quick of k. What does this equal? Plug in 0, what do you get? 0. Plus what you get when you plug in 1 is 1. Plus what you get when you plug in 2 is 2. We stop when we get to our end. Plug in 0 for k, add it to what you get when you plug in 1 for k, add it to what you get when you plug in 2 for k, stop. We plug in 2. That's equal to 3.
Okay, now do it for that one.
For this,
Yeah.
you want me to expand that out? Jeez.
No,
So we got n choose 0, x to the n, y to the 0, plus n choose 1, x to the n minus 1, y to the 1, plus n choose 2. Do I need to keep going?
Okay, I see.
Just what you get when you plug in 0 to that, plus what you get when you plug in 1 to that, plus what you get when you plug in 2 to that, all the way to, let's see, x n minus 2, y to 2, plus what's my last term going to be?
1 minus n.
You instantly fail this class if you do not tell me what this term is going to be.
Y to the n. Okay.
Start out with your first term, your coefficient. This thing, what's that going to be?
N to the n.
N choose n of
X to the 0.
x to the 0,
Y to the n.
y to the n. Right. That's the expansion of that thing. You're scared by these things? Here's a formula for it. Or your calculator knows how to do it. Or you can Google using the words 5 choose 3, and it will spit out the number for you. Okay? That's binomial theorem. Okay, so we're expanding this thing out.
Right.
Good? Erase all this. Maybe I'll keep the binomial theorem part for a second here.
But delta x is y though.
I have this plus this all to the n. How do I do it? That's equal to, let's expand out this term. What's our first two? It's going to be n choose 0, x to the n, delta x to the 0, right?
Yes.
Plus
And choose 1.
n choose 1,
X
x to the n minus 1, delta x to the 1. This is kind of in like, kind of up here. So, x plus y to the n is equal to the sum from k equals 0 to n choose k, x to the n minus k, y to the k. Okay. And then, plus, what do we have after this? I'm not going to write out all these terms, so I'm just going to cut my sum short. We did the first two terms, right?
Yeah.
Plus the next, so we did k equals 0, k equals 1, so whatever you get from k equals 2 on and this whole thing.
Why? Just because you'll manipulate it.
These are the only two terms that we actually care about. All these terms are going to end up going to 0.
Okay.
Which you'll see in a second. Okay, minus x to the n, maybe put parentheses around this like the sum ends there, all over delta x, right?
Mm-hmm.
What is n choose 0? How many 0 element sets can you make from an, how many 0 element subsets can you make from an n element set?
0.
Huh?
1.
1, the empty set. Or if you want to think about it in terms of its formula, n factorial over n minus k factorial, what do we get when we plug in 0 for k?
N factorial over n factorial, which is 1.
Which is 1. So either way, this is 1, right? And delta x to the 0 is
1.
1. So we end up with just
X n.
x to the n. Okay, plus n choose 1. How many 1 element subsets can we get from an n element set? Or what do you get when you plug an n into there?
N factorial over n minus 1 factorial. So just n.
So just n, perfect. N times x to the n minus 1, delta x, plus whatever all these terms add up to, k equal to 2, n choose k, x to the n minus k, y to the k, that whole sum, and then we have minus x to the n. All over delta x, right?
Yeah.
Anything weird in that step?
Just confused where.
Everything's weird? All we did was simplify this term and this term. I didn't change anything with this.
Oh, okay.
That's just a big lump. This we made way different, you'll notice.
I was like, what the hell?
Okay, so you follow everything? Okay. Now, x to the n and x to the n, those
Cancel.
add up to 0. Right? And then we're left with all these terms.
Which are 0.
They're not 0. But I'm going to factor a delta x out of all these terms. Oops, I put a y. I've been doing y this whole time. Wow, you guys, you let me do that. Delta x.
Yeah. I didn't notice that.
Right? Okay. Now, each terms are going to factor out, and are going to cancel out, and I'm going to factor a delta x out of all these terms.
So it's going to be delta x k minus 1.
So I've got delta x times
Plus.
n x to the n minus 1
Oh, I see what you're saying. Plus.
plus the sum from k equals 2 to n of n choose k x to the n minus k delta x to the k minus 1, because I took out a delta x from every term. So now there's one less in there than there otherwise would have been. Does that make sense? Okay. So, plus that sum all over delta x.
Oh, makes sense.
Now, remember, the limit as x approaches x naught is how we got the limit of delta x approaches 0. Since x is never actually equal to x naught, delta x is never actually equal to 0. Right? So, we can divide these two things out. These two things can cancel. We're not dividing by 0, in other words. So, this is equal to, and I've lost my limit along the way, but we were doing the limit the whole time, right?
Yeah.
The limit as delta x goes to 0 of n x to the n minus 1 plus the sum from k equals 2 to n choose k x to the n minus k delta x to the k minus 1. Notice every single one of these terms are going to have at least one delta x in them, right?
Right.
The first term has 1 delta x, the next term has 2, the next term has 3, the next term has 4.
It's going to 0, so can you cancel all that out?
Right, so when we take our limit, every term in here goes to 0. And what does this go to when we take the limit as delta x goes to 0?
Itself.
Itself. Right? Just as we predicted. So it came out as expected. Everything came out nicely. You guys might hate that this term came up.
This might be easier to prove.
No, the other way, you just use the other one.
Yeah, I know.
The other way, you factor out of x to the n minus y to the n.
We'll see about what it proves.
So, if you're less comfortable with the binomial theorem, more comfortable with factoring out of the difference of n powers, then you can do it the other way that we did it. But there you go. There's the proof using Leibniz notation. Crazy. Next is oh, my book jumped on me. Suddenly talking about integrals. Chapter 3. Come on, come on. Need marker. It's not reading my page count. It's showing behind. Okay, we did that. What's the next proof they do? Derivative of a constant is equal to 0. Okay. So, if y is equal to a constant, then the derivative of y with respect to x is equal to 0. Understand what we're proving?
Mm-mm.
Huh?
No.
Y is just a number, like 7. It's constant. If y is equal to 7, what's the derivative of 7?
Oh, okay.
That's weird because it's the derivative of y in respect to. Oh, x is part of the constant, just x to the 1 or x to the 0. Look, where I'm getting confused is it's the derivative of y with respect to x.
I haven't proved this yet.
What I'm saying is there's no x.
Well, yeah, it's just a constant.
Okay, maybe I am.
Alright, so we need to take the limit as delta x, no, dx, delta x. So delta x goes to 0 of, when we plug in x plus delta x into this equation, what do we get?
Y.
Maybe I'll write this
Y
out
plus-
explicitly for
Y
you.
plus.
Y plus delta y
Yeah.
minus y over delta x. Okay, this is what we need to take, right?
Why?
This is a definition of a derivative.
Oh.
Now we need to plug in our function. So this is very generic, and then we keep plugging in the
So
function
C.
over and over and into this thing. Alright, what is y plus delta y of this function? When I plug x plus delta x into this, what do I get?
C. What?
C! Look! If f of x is equal to 7, and then what's f of 100 equal to?
7.
It's equal to 7! What's f of x plus delta x equal to?
Y.
7.
Or C.
7!
Oh.
So, when I plug x plus delta x into this function, what do I get?
C.
C. When I plug x into this function, what do I get?
C.
C.
Okay, you gotta remind us about that.
And then take the limit as delta x goes to 0 of 0 is
0.
0.
You have to remind us of the process again. So y.
So this should have been limit as delta x goes to 0 of that is equal to the limit as delta x goes to 0 of that is equal to 0. Now what do we mean by the process?
Where do we start to get x plus? Tell me if I'm wrong. We start to get x plus delta x when we're plugging it into the function. Because up there, like if you go to the end, at first, if you had written one step earlier, it would have been y
So
plus.
let's just explicitly say what we're doing. We're always taking the limit as delta x goes to 0 of y plus delta y minus y over delta x, where y plus delta y is equal to f of x plus delta x, and y is equal to f of x.
See, that's where we got confused. So now it makes sense that c is c because we're getting f of x plus delta x. Okay.
picture again? Good? Okay, so the limit of, so another way you might see this is the derivative of a constant with respect to x is equal to 0. Okay? Moving on. What's the next? My book keeps jumping to that page. Weird. Very naturally wants to be there. Now we're going to do the derivative of a function times a constant. Okay. Here's where we're going to introduce other variables that represent a function. And maybe I'll start by writing an example, and then we'll do the actual thing. So if I say y equals 3 times some function in terms of x, such as x cubed, then that is equal to 3 times the derivative of that x cubed with respect to x. Which is equal to, then you take the derivative, 9x squared, right?
Right.
The point being, we could pull out this constant. So if we have a constant times a function in terms of x, we can pull the constant out of the derivative and just take the derivative of the function of x.
Right.
Okay? So if y is equal to some constant times, we typically use u as for a function in terms of x. So use just some function in terms of x. If y equals that, then the derivative of y with respect to x is equal to c times the derivative of u with respect to x, is what we're going to say.
Because u is just a function in terms of x.
Yeah, we're using just a function in terms of x. So we can pull the constant out. And I tried to represent exactly what we were saying right there. You understand what we're proving?
No.
You understand, so you understand how all of this is okay. So we said that if you have y equals, should have an equal sign there.
All of it makes sense, I just don't know what.
Let me make my board actually tell you two stupid. If this is true, this implies that the derivative of y with respect to x is equal to 3 times the derivative of this part with respect to x is equal to whatever it's equal to. So what we're saying is if you have y equals c times u, where u is a function of x. In other words, where u is equal to some function of x, like x cubed. It's just some function of x. In this case, u is equal to x cubed. So if you have y is equal to a constant times some function of x, then the derivative of y with respect to x is equal to that constant times the derivative of u with respect to x. Make sense? In shorthand, we're saying we can pull constants out and take the derivative of whatever we mean. That's what this is saying.
Okay.
Okay. So let's do this. So what are we taking? Taking the limit as delta x goes to 0. Y plus delta y minus y over delta x. Right?
Yeah.
What is y plus delta y?
It's f of x plus delta x, which is just going to be x.
Well,
Well, it's going to be
let's
u.
write u as g of x real quick, because we'll think about y as f. How do we do it here? Remember, this is what we're doing.
It's what you're putting to the function.
So if y is equal to c times some function in terms of x, then y plus delta y is going to equal c times g of x plus delta x, right?
Right.
What is g of x plus delta x going to be if we say u equals g of x? So now let's rewrite the same thing with u instead of g of x. So we have y equals c times u. So then y plus delta y is going to equal c times u plus delta u.
No, that's
Keep
not
writing
right.
lines.
Doesn't seem right.
What is u plus delta u? It is g of x plus delta x. If u is equal to g of x, then u plus delta u is equal to g of x plus delta x. This is how you're going to have to make these substitutions. These substitutions are the weird part.
Okay, so just like y of delta y equals f of x plus delta x is the same reason why this is happening.
Yeah,
I'm looking at this like u of delta u is almost like your y.
yeah, y is representing some function. U is representing some function. Anytime you have representing some function, the fact that we use y or u is irrelevant. The point is some function. Anytime we're writing the function plus its change, what do we mean? We mean the value of this.
Yeah.
Right? If you were to plot u, here's u, whatever it is. Here would be x. Here would be x plus delta x. What would we mean by u at this point? We would mean,
U plus delta u.
yeah, u plus delta u would be this point, which we would represent if this function was g of x. That's the same thing as g of x plus delta x.
Okay.
Same exact thinking. Anything weird in that? Okay, so this is a substitution that we need to make. That's the hard part. Remember how you substitute. So this is going to equal, see if you can follow me on this, c times u plus delta u minus c times u.
So where's our constant? Okay. Where does our
C.
constant come from?
Y is equal to c of u.
Okay.
Here's what we're doing.
I think where we
If y is equal to c of u, we're proving that dy dx is equal to c times du dx.
Okay. In your limit over there, shouldn't you have a c in that? C in front of the
No! Y is equal to c times u. I'm substituting it for y. You always start, doesn't matter what your function is, you always start with this. Every time.
Okay.
Then the hard part is figuring out what do you plug in right here. Right? Because this part you typically know how to do, and it's finding this over and over again. What is y plus delta y?
Let me think about it. Y equals c times u.
So let's write this out. Let's be super explicit. Really quick, I'm going to write y is equal to f of x is equal to u times c. But then I'm going to do u is equal to g of x. Good? Which gives that y is equal to, I'll do the g of x first. G,
Of x
I
times
keep going to do q. G of x times c, right? You good with all that? So remember, what is y plus delta y? It is what you get when you plug in x plus delta x. So this is equal to f of x plus delta x, which is equal to c times g of x plus delta x.
I see that all done.
Now, if y plus delta y is equal to f of x plus delta x, then u plus delta u, for the exact same reason, is equal to g of x plus delta x, right?
Right. If u is just representing the g of x function, well, u respect at x.
For the exact same reason that this represents this represents this. If we were to plot this function g of x, if we were to plot this function, then this would be the change in u's height when we change x by that much. For the same reason that this is a change in y's height when we change x by that much. Still weird? Let's come at it backwards. Let's say that I have u is equal to g of x. Okay? Then u plus delta u is equal to g of x plus delta x. Good with that?
Mm-hmm.
Okay, then say y is equal to u times c. Or in other words, f of x is equal to g of x times c. Same thing on both sides, right? So y plus delta y is equal to, I don't know, but it's equal to the same thing as f of x plus delta x, right? Which is equal to, when you plug in x plus delta x, what do you get? You get g of x plus delta x times c.
Okay.
Okay? Is it clicking? Is this helping?
A little bit.
I mean, we're just doing the exact same thing. You're just like doing it twice.
I know, it makes sense.
I'm out of ways to explain it. Without just going back and redrawing our picture. I mean, it's all for the same reason that this, we define this to be this. And so delta y ends up being this thing. If that were u, delta u would end up being this thing. Here's another way to think about it. Y is just u times a constant, right?
Okay.
So if y changes by, it's like scaling it up, right? So before you had delta u, you only changed by this much. If you times the whole thing by c, delta u just got a whole lot bigger. So delta y is going to be delta u times that constant.
Okay.
That makes sense? So if u is just this function, and y is taking that function times it by 3, y is going to look something like this, right?
Yeah.
So if this over here was delta u, then over here, I didn't line it up very well, let's pretend that this lined up with that. Then over here, that same thing, delta y, is going to be the same delta u times a constant. So when you multiply this out, it turns out y plus delta y is equal to u times c plus the change times c. Is that helping? No. Okay, forget that. Repeat, I guess. You're good with this.
Yeah.
So we define, when you change the input in the function, whatever comes out, we're calling this whole thing where this was a change. We went from y to y plus delta y when we added this much. Same exact thinking. If u is a function in terms of x, just like f was a function in terms of, or just like y was a function in terms of x, then when you change the input by this much, the output changes by this much. Right? So you're good with u plus delta u is this.
Yeah.
Okay. Now we define y to be u times a constant.
Okay.
In other words, f of x is g of x times a constant. So then, the question is, what's y plus delta y? It's what you get when you plug x plus delta x into this thing.
Okay.
Y plus delta y is f of x plus delta x. So y plus delta y is f of x plus delta x, which is, look at what f of x is, it's this. It's g of x plus delta x times a constant. That's what f of x is. So plug that in. And what is this? This is exactly our u plus delta u. It's u times how much u plus how much u changes when you plug in delta x.
Okay.
Is that clicking?
Yeah.
So you're good with this? Okay. So here's our substitution, and you're good with the substitution over delta x?
Okay.
Good. And equal to a limit, obviously,